ABCD is a quadrilateral with AD equals BC. P is the intersection of its diagonals AC and BD. E and F are on side AD and BC respectively with BE equals DF. The segment EF intersects the diagonals BD and AC at Q and R respectively. Consider all triangles PQR as E and F vary. Then the circumcircles of this triangle has a common point other than P. Find the point and prove it. Let's look at a demonstration. As E and F vary but keep BE equals DF. The position and the size of the circle keep changing, but it always passes a fixed point O here. How to construct or identify this point O? During the actual competition, students didn't have the luxury to run such an animation, but they can use two pairs of E and F to draw two circles. These two circles will have two intersections. One is of course P, the other one must be the target O here. Let me review the answer. O is actually the intersection of perpendicular bisectors of two diameters, AC and BD. So, the objective would be to prove that point OPQR are cyclic. First of all, O is the perpendicular bisector of AC. We know every point on the bisector is equidistant to the endpoint of the segment. Therefore, OA equals OC. These two segments is colored green. Similarly, OB equals OD, the red segment. We are given a condition that AD equals BC, the blue segment. Then triangles OAD and OCB are congruent because each triangle contains a blue segment, a red segment, and a green segment. So, side-side-side theorem applies. As a result, angles ODA and angle OBC are congruent. I'm going to use it right away. It is also given that BE equals DF. Then, by side angle sides theorem, triangles OBE and ODF are congruent. As a result, the third pair of corresponding sides OE and OF are congruent. They have a brown color. Now look, the point O really play a central role here. OA equals OC, and OB equals OD, OE equals OF. Moreover, if we rotate triangle OBC around O for a certain angle, it will completely coincide with triangle ODA. Question: what is the rotation angle? We can measure it in three different ways. First, look at the green segment OC. It is rotated all the way to another green segment OA. So the angle should be measured as angle AOC. Similarly, the broad segment OE is rotated all the way to another broad segment OF. So the angle should be EOF as well. And of course, it can also be measured as a red angle BOD here. Three angles measures just one rotation, so they must be the same. Therefore, these three angles are congruent. If we don't use this rotation, we can also establish the equality by angle chasing. We have two pairs of congruent triangles, not a big deal at all. Immediately, we have three similar triangles AOC, EOF, and BOD for two reasons. First, they are all isosceles triangles, and secondly, their top angles AOC, EOF, and BOD are congruent. As a result, their base angles are also congruent. They are denoted as alpha. Each isosceles triangle has two base angles, so there are total 6 alphas. We are almost done. The rest is just angle chasing. First of all, quadrilateral ODFQ is cyclic because of the two alpha angles at point F and D. The inscribed chord theorem applies. Because of the same theorem, angles DFQO and DQO are congruent. They are denoted as beta. Similarly, quadrilateral OCER is cyclic because of the two alpha angles at point E and C. And for the same reason, two angles CEO and CRO are congruent. They are denoted as gamma. We have another angle BEO with measure beta. Why? Because triangle BEO and DFO are congruent. Therefore, angle BEO equals angle DFO, which has measure beta. Now, look at the beta and gamma at the point E. They sum up to a straight angle BEC, which is 180 degrees. So beta plus gamma equals 180 degrees. Finally, quadrilateral OPQR is cyclic. This is our target. Why? This quadrilateral has two opposite exterior angles at Q and R. The exterior angle at Q has a measure beta. The exterior angle at R has measure gamma. They sum up to 180 degrees. Therefore, this quadrilateral is cyclic and the proof is done. Just one more thing, an exercise. This is an alternative version of the problem. ABCD is a quadrilateral with AC equals BD, the two diagonals. And the E and F are on AC and BD respectively with AE equals DF. The line EF intersects two sides AD and BC at Q and R respectively. O is the intersection of perpendicular bisector of two sides AD and BC. Consider all triangles OQR as E and F vary. The circumcircles of this triangle have a common point other than O. Identify this point and prove it. This version is easier than the original one because the target fixed point is easier to identify. Try it. You would need two pairs of congruent triangles, three similar isosceles triangles, and angle chasing. Thank you for watching.